Okay. So let's go through this. So here at 0, we have our TMS. Let's just go through everything here. There's our TMS at 0. We have 2 signals. I see 2 signals, so I know I have 2 different kinds of hydrogens. We have a signal at right at 4 ppm. If you look at your summary chart that I gave you, 4 ppm is protons on a carbon connected to an electronegative atom. And I have an electronegative atom, that's my chlorine there. So we have protons on a carbon connected to an electronegative atom. That's what's coming here at 4. I have a signal here at 5.8. You look at the chart, 5.8, that's protons on a carbon of a double bond. What happened? I don't have a double bond. Why do I have a signal at 5.8? My chart says double bond. Hydrogen on a double bond.
2 chlorines.
It's because there's 2 chlorines here. So that's what I was trying to get over to you there earlier. Don't get locked into thinking it has to be this. So if, on my chart, if 1 chlorine, so normal alkanes come down here, and if 1 chlorine shifted me to here, 2 chlorine is going to shift me to here. If you've got 3, it's going to shift you even further. 3 chlorines, actually, the proton comes at 7.24 if you got 3 chlorines on there. So they get shifted even more. So don't get locked into thinking it has to be this. This is just a good starting point. So these got shifted all the way down here to 5.8 because that's a proton on a carbon with 2 electronegative atoms. I didn't have 2 on my chart. I had 1. 1 got you to 2.5 to 4.5. But if you got 2 electronegative atoms, it gets you shifted even further. Okay. Now, so we got that chemical shift figured out. Let's look at the integration. You can see the integration here. This is integrating. You can see this is exactly twice the size of that integration line. Integrating from 1 to 2. You can just eyeball that. You don't even have to look at the numbers. You can see that my integration, this is twice as big as this one. So integrating from 1 to 2. That matches what we have there. So if you're integrating for 1, more than likely that's a CH group. Integrating for 2, more than likely that's a CH2 group. And then lastly, we look at the splittings. So this one here's an expanded view. You can see it's a doublet. That's telling me that my neighbor only has 1 proton. Because if it had 1 proton, that would split me into a doublet. This one is a triplet, so that's telling me my neighbor has 2 protons. Because if you plug 2 into the formula, you get 3. So because I'm a triplet, I know my neighbor has 2 protons. Okay, so everything worked out there with this one, with the spectrum. You can see everything matches. Let's look at another example or 2 here with the splitting. So here's another example. You got 2 different kinds of protons. You have the red one and then the blue ones. So I get 2 signals. I've got 2 different kinds of hydrogens. I get 2 signals, and then your splitting is due to your neighbor. So we get a signal for the red, and it's going to be split by the blue ones, by its neighbor. There are 6 blue ones, so we'll plug 6 into the formula, 6 plus 1. This will show up as 7 lines, a septet. That red one will show up as 7 lines, it's a septet. We also get a signal for the blue protons, and they're split by the red proton. That's their neighbor. There's only 1 red one, so we'll plug 1 into the formula. 1 plus 1, it will show up as a doublet. All of those blue ones show up as a doublet. They come at the same place, and they show up as a doublet. Because they only have 1 neighboring proton. Now, the next thing we're going to talk about is Pascal's triangle. Let's say I've got 3 lines showing up there on the spectrum. how do I know if those three lines belong to each other? If that is a triplet, or maybe it's a doublet and a singlet that just happen to be kind of close to one another. So is it a doublet and a singlet, or is it a triplet? Do they all belong? The way we figure that out is to use Pascal's triangle. Now, you learned Pascal's triangle in one of your math classes. I don't remember, maybe linear algebra, maybe. I can't remember. I know I had it in one of mine. Anybody remember? Anybody had Pascal's triangle in anything?
It's in trig.
Is it in trig? Okay, trig. I couldn't remember. I knew it was in one of the math classes of some kind you covered. Okay. If you don't remember, I'm going to show you how to generate Pascal's triangle. It's given by the coefficient of the binomial expansion of a plus b to the nth power. But it's really easy to just generate. So you have your triangle. You'll have ones on the diagonals of the triangle. So you bring down, start here at the top with the 1 at the top. You bring down 1 and 1. You go down to the next level. You bring down the ones on the diagonal. And then the middle number, you add what's above it. So 1 plus 1 makes 2. Bring the ones down on the diagonal, add what's above it. 1 and 2 makes 3, 2 and 1 makes 3. Bring the ones on the diagonal, add what's above. 1 and 3 makes 4, 3 and 3 makes 6, 3 and 1 makes 4. And you can keep building your Pascal's triangle. Now, what Pascal's triangle gives us, it gives us the relative intensities of that splitting. So if we have a doublet, those two peaks of a doublet should be about the same size. Pretty close to being the same size. Nothing's perfect. This is saying they should be exactly the same size, but nothing's always perfect. But they should be pretty close to the same size if it's a doublet, if they belong together. A triplet, so I used a triplet there as my example a moment ago. I had the markers, and I said a triplet, is that a doublet and a singlet, or is it, do they belong together? If they belong together, then what this is telling me is that the middle line should be twice as big as the two on the outside. And the two on the outside should be about the same size. So, there, look at the top of my markers here, there would be a triplet. The middle one is twice as big as the ones on the outside. The two outside ones are about the same size. That's a triplet. If it looks like this, that's not a triplet. I can't get my markers to stand. There. That's not a triplet. There's three lines there, but that's not a triplet. They don't belong to one another. Because these two are the same size, and this one, yeah, it's bigger, but it's out here on the edge. A triplet is the middle one that should be twice as big as the two on the outside. So I know these don't belong together. These two are about the same size, so that's probably a doublet and a singlet that just happens to be close together. These look like they're the same size. That's a doublet, there's a singlet, and they just happen to be close to one another. Okay, so you can use that Pascal's triangle to figure out, are those true splittings, do they belong to each other, or are they just two signals that happens to be close by to one another? Now, be careful. Now, like this one here, the example I have up here, these are colored different. Got a red and a blue. You can color anything you want to. But these are not different. They're on adjacent carbons, but they should have actually both been red or both been blue, because it has symmetry down the middle. They are equivalent. Equivalent, remember what I said, equivalent protons do not split each other. So these would show up as a singlet. They are not going to be split. Even though they're adjacent protons, they will not be split. You don't split, equivalent protons don't split each other. Equivalent protons is like splitting yourself. You're not going to do that. Or splitting your twin brother or whatever. You're not going to do that. So those two are actually equivalent. They should have both been red or both been blue. That was a mistake there. So just be careful. Now down here, these are actually different. Because see, these are different. There is no symmetry. This carbon's got 2 chlorines, and this one's got 2 bromines. So these are different. But up here, these two are equivalent. So equivalent protons do not split. Non-equivalent protons will split each other. This is going to split that one into a doublet, and that one splits that one into a doublet. Okay, so the top one shows up as a singlet. The hydrogens there show up as a singlet. Down here, they show up as a doublet. Now, the next thing I'm going to deal with here is protons on other atoms. So if you listen carefully to what I said, I'm going to simplify things. For our purposes here, for organic, the only protons that are going to do any splitting or be split are protons on carbons. They need to be on an adjacent carbon. Protons on oxygen or nitrogen typically do not split. So for our purposes, we're just going to say they don't split at all for this organic class. So if you're on a nitrogen, oxygen, anything else, just forget about it. They don't split. It's got to be on a carbon to do the splitting. Now, the reason these on oxygen or nitrogen, that's mostly what we deal with, those are acidic protons. And acidic protons are coming on and off so fast. Remember, acid-base is really fast. And so they're coming on and off so fast, any acidic proton, coming on and off so fast, it's happening faster than the NMR can operate. And so our NMR does not recognize any splittings from those. So here is the speeds at which your exchange is happening, where the hydrogen is coming on and off. And there's the speed the NMR is operating. So that exchange, that proton coming on and off, is happening faster than the NMR can operate. So you don't typically see a splitting from an OH. It's not going to split any other hydrogens, nor will they be split by any other hydrogens. So again, for our purposes of this class, only hydrogens on carbon are going to split each other. Now, that finishes what I wanted to talk about there with protons. So let's go through and talk about how to interpret a proton spectra. So we're going to go through an example here. How do you actually go through? First thing I'm going to do is same order as what I went over all this stuff. We're going to count the number of signals that we see and to figure out how many different kinds of protons we have. Now, you may have some signals overlapping, but just for the moment, let's just pretend that we don't have anything overlapping. Sometimes we might, but at least we'll get an estimate, kind of just where to start. We'll then look at our chemical shifts. So use your little summary chart here. Look at your chemical shifts and try to get an idea of what you might have there. Then you're going to look at integration. That was next. That integration, that area under the signal, integration, that's going to tell us about the groups. So if it's integrating for 2, more than likely it's a CH2 group. Integrating for 3, more than likely it's a CH3 group. So on and so forth. And then last, look at the splitting. So like I said, save that splitting to last. Take care of yourself first before you start worrying about what your neighbor looks like. Now, after you've done all that, you're going to have some fragments, some pieces that you got to put together. This is like working a jigsaw puzzle. You go through all 4 of these, you wind up all these little pieces. And then you just have to put it together. And so once you get used to working these, I think these are so much fun. They're hard, but once you get used to doing them, they're so much fun to work these. It's just like working a puzzle. So let's look at an example. Now this is a pretty simple example. We're given the formula, C3H7Br, so that's helpful. First thing I'm going to do before I even start on the NMR, if you're given the formula, what's something we've done in the past you might want to do here? You don't know what to draw out. Something we did last semester. Calculate IHD. Remember IHD, index of hydrogen efficiency? calculate IHD and see how many double bonds, triple bonds, that kind of stuff you got. That would be helpful. If you're given the formula, that's the first thing I'm going to do before I even start on my spectrum. So if you calculate IHD here, you see it's 0. So I know I have no double bonds, no triple bonds, nothing like that. No rings. A ring counts as an IHD of 1. So I know I have none of that. It's all single bonds and just straight chain. That's helpful. So do IHD first if you're given the formula. You may not be given the formula. Okay, now, so first thing we want to do is count how many signals we have, and that tells us how many different kinds of hydrogens we have. So if we look, we got here 0, of course, is the TMS. Little peak there at 0. But I see 1, 2, 3 signals. I know I've got at least 3 different kinds of hydrogens. Now with that small of a formula, C3H7, I got 3 carbons, there's probably no symmetry in the molecule. Because I've got 3 signals, I've got 3 carbons, and then there's going to be hydrogens on those carbons, so they're probably all different. That's how come I got 3 signals. So that's giving me some information. If I only saw 1 signal down here, and I've got that formula, I know there's lots of symmetry. Okay, now, the next thing we do, we look at chemical shifts, where things come. Okay, so we got something here at 1 ppm. 1 ppm says that's an alkane. Okay, so that's protons on a carbon that's just all involved in all single bonds. Alkane proton. We got some here at almost 2. When you look at 2, my chart says hydrogen on a carbon next to a carbon of a double bond. Huh? I just calculated IHD and said there was no double bonds. So that's a problem. That's okay. That one makes no sense. We don't have to know everything. We can still figure this out without knowing every single peak. So skip that one for the time being. We'll come back to it. But the chemical shift didn't make sense right there. Okay, let's go to the next one. Okay, this one's at 3.1, 2, 3, 3.4. 3.4 says a hydrogen on a carbon that's connected to an electronegative atom. Hey, I have an electronegative atom. I got a bromine. Okay, that's something I need to know. That's a hydrogen on a carbon that's connected to my bromine. Now, we've got some real pieces there already starting to form. Now, the next thing I'm going to do is look at integration. The integration lines. And this one happens to have the numbers already on there. They may or may not be. If they're not given, you can just eyeball it or measure them with a ruler or whatever. This is integrating for 2 to 2 to 3. And then check it and make certain that adds up to your total up there. So the computer would have said 1, 1, 1.5. And you know you need to get to 7. You'd have to double that to get to 7. Okay, 2, 2, 3. That equals my 7. So with this integrating for 2, I'm going to guess that's a CH2 group. This one's integrating for 2. I'm going to guess that's a CH2 group. This one's integrating for 3. My first guess is that's a CH3 group. So let's write some of this down. So we said this one here, integrating for 2, we said that's a CH2, and based on the chemical shift, we said this is the one that's next to the bromine. So this is a CH2 that's connected to the bromine, to the electronegative atom. That's what shifted this down here. So I've got a CH2 connected to a bromine. Write that down. There's a piece of the puzzle. This one here, it's integrating for 2. That's a CH2, but my chemical shift, that didn't make no sense, so I don't know what's around it, but let's just write that down. I got a CH2. I'll put a question mark for that. We don't really, that one's kind of confusing to us at the moment because of the chemical shift. This one is a CH3. Normal alkane was what the shift told us, just a normal alkane proton. So CH3. So write that down. Now, I've got some pieces there. We're starting to form, but we can probably see a little bit more. Let's go to our splitting. Save the splitting to last. Now I have an expanded view up here so you can see these a little bit better. Let's look at this one we just did, the CH3. If you look at the expanded view, I think you can see it here. This is a triplet. It's a triplet. 3 lines. That's telling me what my neighbor looks like. Those 3 lines is telling me what my neighbor. So we know this was the CH3 based off of the integration. And then that triplet tells me what my neighbor looks like. How many protons is on my neighbor? 2. 2 would make it a triplet. So I know next door there is a CH2. Now let's go look at our next one. This one here, I don't know, that's kind of a mess. I can't hardly see how many is there. But that one was confusing to us before anyway, so let's just skip that one. We don't have to do that one. We can get it from the rest of it. This one over here made sense. This is the one with the bromine. And it is a triplet. So I know what's next door on it. Next door, there has to be a CH2. Okay, I've got enough now. I've got enough of the puzzle. I can put it together and see what the picture is. See what the structure is. Let's start trying to piece this together. So we know we've got 3 carbons all total. And I've got more than that drawn here, so some of these are the same. I've only got 3 carbons, and I drew out 5 over here. So some of these are the same carbons. But our full formula, this is CH3 next to a CH2 that's next to a CH2 that's connected to a bromine. There is my structure. If you start piecing these together, these 2 CH2s are the same ones right there. So I didn't even need this other thing down here. Those 2 are the same, and then that gives me 3 carbons. Now, that one was very easy. That's a 1 bromo propane. There's only one other option for this. It would be 2 bromo propane. 2 bromo propane would have symmetry down the center, and so you'd only have 2 signals. You'd have 2 signals. This one's got 3 signals. So that one was very simple. Now remember we had trouble with this one here. So if we just double check ourselves here, that one is the metal carbon here. And so it's got 3 hydrogens on this side, 2 on this side. It's got 5 neighboring hydrogens. 5 would split it into 6 lines. This should be 6 lines. And I think now you can probably, if you know it's 6, you can probably count them. There's 1, 2, 3, 4, 5, 6. Yeah, there was 6 there. A little bit hard to see, but especially when I know it's 6, what I'm looking for. You can see it easy. Now that chemical shift kind of confused us because these up here look like a hydrogen on a carbon next to a double bond. But if you look at the structure, so the bromine here shifted these hydrogens on this CH2 all the way down to here. But then it shifted the hydrogens on this CH2 just a little bit. Here's where a normal alkane comes. And if you're a hydrogen on a carbon attached to that bromine, you got shifted all the way down here. These are just kind of close to the bromine, so these feel the effects of that just a little bit. So they get shifted just a little bit outside of their normal range. That should have been an alkane proton, should have been right there, but they get shifted just a little bit because they're kind of close to the bromine. So like I said, don't get locked into my chart. This is very helpful, but realize this is just a starting point. Okay, questions? Okay, so that's how you work through one of those. You just have to play around with it, start getting some pieces of the puzzle, and you build those up. Now, I want to point out a couple of problems here, some complicating features. We occasionally have peaks that overlap with one another. That's just by pure accident. They occasionally come on top of each other. Nothing we can do about it. Here are some peaks that are coming on top of each other. How do I know they're coming on top of each other? I already talked about that. you use Pascal's triangle. Looks like there's 4 lines, looks like a quartet. 4 lines would be a quartet. Do they belong together? No, because Pascal's triangle says if it's 4 lines, the 2 outside ones should be the same size, the 2 inside ones should be the same size, and the 2 on the inside should be 3 times as big as the ones on the outside. It should be a 1, 3, 3, 1 if it's a quartet. A 1, 3, 3, and then that's like 10. That's not a quartet. Actually, what's happening is it is a quartet. It just so happens that it's a singlet and it's a quartet that are overlapping. That singlet's overlapping one of the lines of the quartet. So it does make sense. It's a 1, and that's like 3 times as big as that. So 1, 3, 3, and the other one should be small. Should be a 1 there, but there's a singlet that's overlapping that one. So sometimes you have peaks that overlap. Nothing you can do about it. Now there is a way to avoid that, is go to a stronger magnet and it will separate those out. So if you go to a stronger spectrometer, you have this happen a lot on a little 60 megahertz instrument, but you go to 500 megahertz or a gigahertz or something like that and it splits those out. Less likely to overlap. So we sometimes will have problems with overlapping peaks. Sometimes they just accidentally come to the same place. You can't do anything about it. So here, all of these aromatic protons, there's supposed to be 3 different aromatic protons. There's 3 different ones there. If you look at the symmetry, there should be 3 different aromatic protons. But I'm only seeing 1 signal here. It just so happens that all of those aromatic protons just accidentally came at the same place. Nothing I can do about it. Now, how do I know what's happening here? One of the things you can do is look at the integration. This would integrate 5 to 3. So if my aromatic region here is integrating for 5 protons, I know all of them are coming right there under that signal. Also, if it's integrating for 5, I know how many groups I have on the benzene ring. If you got 5 hydrogens on the benzene ring, you know you only have 1 substituent. If this is integrating for 4, I know I've got 2 substituents and 4 hydrogens. If it's integrating for 3 down here, I know I've got 3 hydrogens and I have to have 3 substituents. So I know this is the aromatic, I know I've got a benzene ring, and you can look at the integration and see how many hydrogens you have on that benzene ring, and then therefore you know how many substituents you have coming off the ring. You can also use that region. So with your aromaticity, you can also tell whether it's ortho, meta, or para by looking at what's going on. So let me show you that real quick. This is a common thing. Pull this up just for a second here so my camera can see it. I want to cover this real quick because ACS exam loves to do this. Whether it's ACS or MCAT or DAT or something, it's got to be something you can answer pretty quickly. Look at this one. The only one that's got symmetry here is the para. It's got symmetry down the center. You've only got 2 different kinds of protons here. You got these 2, and then you have these 2. So when things are para, this is going to be, these would show up, they would get split by the adjacent, so this would show up as a doublet. These would get split by the adjacent, this shows up as a doublet. You see it, you look down there at the aromatic region and you see 2 doublets, you know It's para substituting. That's so easy. When you have two doublets, you know they are para to each other. If they were meta, let's see what we should see for meta. This one has no symmetry, so I'm going to have four signals for the aromatic protons. All four of them are different. This one would be a singlet. This one would be a doublet. This one would be a triplet. This would be a doublet. If you look at the ortho, it also no symmetry in this one. I would have four signals. This one, it would be a doublet. This one would be a triplet. This one is a triplet. This one is a doublet. So if you look down there at that aromatic region and you see a singlet showing up down there somewhere, along with these doublets and triplets and stuff, the singlet's what really stands out. You know it's the meta one, because the ortho one has two doublets and two triplets. Para only has two doublets. Para really stands out. This is normally what they're going to ask on a DAT or an MCAT or your ACS or something like that. They're normally going to have para, because that one is easy. It stands out. Easy to pick that out. You know, if you're down there in that 6.5 to 8 region, you know you have an aromatic, you know you have a benzene ring, and if you got two doublets, you know they're para to one another. You got two groups para. Questions? Okay, let's see if I can get finished with this. I'm not going to go through all of this of how to typical way to report the way to report an NMR spectra. One thing I'll just say is, when you report signals, you don't report every line in the spectrum. That's too many to report. What you report is the center of the signal. So if you have a triplet, you only report the middle one, and then just say triplet. So if you, like here, this is a signal at 1.02, that's the middle line, and they put a T there for triplet. Now I'm not going to go through the rest of that, but that way you don't have to list so much. If you have a quartet, you always report the center. Well, where's the center? Here's the center. Hey, there's no peak there at the center. What do I do? We'll average two of them. Average the two middle two, or average the two outside two. You average those, and that would give you the center. So you always report the center of the peak and just say what the splitting is. So you report the center and say quartet. This is a signal at 3.4, and it's a quartet. Put a Q there for quartet. That's the typical way to report. If you're trying to write it out, you don't report every single line. That's too many numbers to put in. Okay, so that's proton NMR. We're going to look at carbon NMR now. So I'm halfway done. What? Okay, no, carbon, very short. Now remember, for carbon, it was carbon 13 is the one that's NMR active. Carbon 12 is not. Now, of the two isotopes, carbon 12 and carbon 13, there's only 1.1% carbon 13 in a sample. Of all the carbons, only 1.1% in nature is carbon 13. And only the carbon 13 will show up in the NMR. So, our carbon spectra, they don't give a very good spectrum. To actually get a spectrum, we have to take a lot of scans, because that carbon is about 6,000 times less sensitive than the proton is in the spectrometer, because of that difference in the amount of isotopes there. So you basically, to get the same pretty spectrum like you did for proton, you'd have to take about, for one signal you take for proton, you take one scan and you get a good spectrum. For carbon, to get that same level of spectrum there, same signal to noise and everything, you'd have to take 6,000 scans just to equal that. Now we can do that, and we do. On our spectrometer, to run a carbon, it takes about a day and a half. On your big spectrometers, you can run them faster, say on a 500 megahertz, but it still takes about 6 or 7 hours to run one, even on the big spectrometers. On our small one, it takes about a day and a half. Now, just like we had with protons, for every different carbon there is in the structure, you will have a signal for that. Just like we saw a signal for every different hydrogen. No, don't worry about that. So this one here, there's no symmetry in that molecule. There's no symmetry. So all 4 carbons are different because there's no symmetry. I will have 4 peaks because there's 4 different carbons. And there's the spectra. You can see 4 peaks. Now the good thing about carbon NMR is carbon happens over a much broader range. If you saw for protons we typically scan from 0 to about 12 for protons. That's the range they come in. Carbons occur over a much broader range. They go from about 0 to over 250. From 0 to 250. Now that's nice, having them spread out. That's just the way carbons are. They're spread out over a much broader range. You almost never have, we talk about signals overlapping, you almost never have carbons overlap because the spectra is so broad, so spread out. I have run, probably in my lifetime, I've run over 1,000 carbon spectra, and only twice have I ever had carbons overlap. Out of all of those spectra, only twice have I ever encountered carbons overlapping. So it's extremely rare to have carbons signals overlap. They're really spread out. So we get a signal for each carbon that we have. Now, I'm going to just do a couple examples. I'm not going to do all this, but just real quick. Let's see, where was I at? Now remember, we're looking at carbon now, so let's just do 1 or 2 of these. Let's do M. How many carbon signals should I have for M? How many different carbons do I have in M? Look for the symmetry. Okay, 6. Let's see what we got here. 1, 2. These 2 are equivalent because of the symmetry. 3, 4, 5, 6, 7. I would have 7 signals in the carbon NMR. How about L right above it? I mean carbon. You got symmetry right through here. 4. Okay, let's see. 1. These 2 are equivalent. 2, 3. Those are equivalent. 4. Those 2 are equivalent. That's got 4 because of the symmetry. Like for K, none of those, there's no symmetry, so all of those are different. So you got 1, 2, 3, 4. You'd have 4 for that one. They're all different. So you use the same thing as what we did with protons there. Just remember you're looking at the carbons. So you'll have that same type of thing. Questions on that?
Do instrumental people need to know carbon?
Yeah, but I'm going to give you all more.
Gotcha.
We're going to look at a lot more stuff.
Yeah.
So remember the basics, yeah. I guess that's okay. Where am I at? Okay, so this is where I just went through. Okay. Now, chemical shifts, where they come on the x-axis is going to matter. You have the shielding and deshielding, same type of thing going on. Electronegative atoms will shift things downfield. So if you have, a carbon with a bromine on it or a carbon with an oxygen on it, they get shifted downfield. Hybridization of the carbon matters. Now this is a weird order. I can't explain it, but this is the order that you have for your carbons. sp3 is going to be the most upfield here. They are going to be at the lower ppm values, would be your sp3 carbons. And then you have sp hybridized carbons. And the furthest downfield are the sp2 carbons. They're at the highest ppm values. Don't know why it's that order, but that's the order that we have them. Here's some numbers. You can kind of see that follows that. So you have the sp3, most upfield, lowest ppm values, and then your sp, and then your sp2 is the furthest downfield. Now here's a chart of where things come. I don't like it this way. I like it sideways. So this makes more sense. So this is similar to what I gave you with the proton. Here's just the carbon version. So we have normal. This is all I remember. You don't have to remember exactly what all these are. We have sp3 carbons, here from about 0 to about 50 or 60, sp3. If they happen to have an electronegative atom on them, they get shifted just a little bit. So if you got an oxygen or a bromine or a chlorine, something electronegative, you get shifted just a little bit downfield. So sp3, and then if you have an electronegative atom attached, you get shifted a little bit. And then we have our sp. sp is typically from about 70 to about 90. You can have an sp further if you have, say, a nitrogen on there. Here's an sp hybridized carbon with a nitrogen on it. So that gets shifted further because of that electronegative atom, the nitrogen. But primarily, we don't rarely see those. Primarily, here you go, 70 to 90 is normal sp hybridized carbons. Now, from about 110 to about 150 are aromatic sp2s and alkene sp2s. There's your sp2. It's alkenes and aromatics. Unfortunately, we can't tell the difference in them like we can in proton. Proton, you can tell the difference in those. Carbon can't. Now, the furthest downfield, these are also sp2, but this is carbonyl carbons. These are sp2 carbons, but they're all carbonyl. So from about 150 all the way up to 200 and something is carbonyls. You don't have to be concerned about whether it's an ester or an amide or an aldehyde or whatever. Just remember it's a carbonyl. 150 and higher is carbonyl. That's good enough. That gives you a lot of information. So just remember 150 and higher, all the way up in the 200s, carbonyl carbons. That's enough for you to know. sp3 with electronegative atom gets shifted a little bit. sp, sp2, and then the carbonyl sp2s furthest down there. Know that. Okay, here's another example. So this one has got 3 different carbons. I see 3 signals. We got TMS reference. You got 3 signals from the 3 different carbons. And there's a solvent. Why is my solvent showing up? It's deuterated. We're looking at carbon NMR. The carbon will show up. Deuterium does not in the proton, but we're looking at carbon, so that carbon does show up. I will see a solvent peak in carbon. Okay, that is it. Now, let me just say, so we can't do integration on carbons because there's just not enough carbon-13 in there. Your integration isn't very accurate. You can't do, we turn the splitting off. We don't do splittings. We turn that off. You can do that on the computer. We turn off the splittings because it's not too good either. Because, you know, what's the likelihood of having your neighbor, you know, it's hard enough to find a carbon-13 period, let alone a neighbor with carbon-13. We turn all that off. So, there's just not as much information. So we got the number of carbons, gives us the number of signals, different carbons, and then you have the chemical shift, gives you a little bit of information, and that's it. That's all you got. Now, the last thing I'm going to do is give you an assignment. This assignment will be due Friday of next week. I know on the sheet it says due 1 week from the day, but I already printed these up, and yesterday's lab talked me into doing Friday. They said you all had a bunch of you had a cell test next week, and we got the lab midterm and some other things, and so they talked me into doing Friday. So I'm just going to make it due Friday for everybody. You can thank Tuesday's lab for talking me into it. Now, if you're all with instrumental, you can go ahead and leave. I'm just going to pass out the assignments here. I need you to tell me which, if you're in one of the other lab sections, I need to know that. So, is anybody in here today from my Tuesday lab section? Just those two? Okay. Okay, pick one. They're different.
Okay.
I don't want you to say I gave you the hard one. Pick one. Are the rest of you from the Wednesday section? Okay. Everybody else is from the Wednesday section. Okay, I got to make certain I give you the right one because I've given Lee here the answers to these, and if I give you the wrong one, he won't have the answer to it. He can't grade it. Now, these are different, so I don't want you to say I'm giving you a hard one. So I'm going to ask you to cut the deck. Now, he cut the deck, so if you get a bad one, you can blame him. Yeah. Now this counts for 25 points. It counts the same as a lab report. You do get one drop lab, so if you really screw this up, it can count as your drop. It is hard. I know it's hard. So it can count as your drop lab. But you need to really try it and do your best because you will see NMR Spectra on the lab final. It will be on the ACS final. And it will be on like DATs and all that. Oh, I forgot to turn my camera off.